Okay, let's get going. Today I'm going to do the first lecture, and what we're going to do is we're going to step through this paper, Newtonian Mechanics of Demand. There's the title, and you can find it at archive. Here's the URL. You just type it in, it comes out. Now, the paper doesn't look that long, but it's very, very dense, and there's a lot of stuff. All right, and it's purposely written like that as a set of foundations. So it's not an easy read, and I divided it up, and I'm going to divide this up in quite a bit of lectures that we can step through and discuss these things and really let it sink in. And I just don't see a way around that, because Newtonian mechanics is, I mean, we get taught it, quite easily here at sometimes it's just a very intricate subject, and it takes a long time to get it. Even then, you don't get it. So now, to do a regular type of engineering, you don't really need that profundity of knowledge that you know where all this comes from. You just need a proficiency with able to solve problems. Right? So if you just do your exam, that's all you need, and you can get away with just knowing that and getting a good grade. But if you do research, the thing turns around, and then you kind of reach yourself, and you realize you can only solve pre-canned problems, but you don't have the level of understanding to do something new. And I see students who've been busy doing it, nodding, this is true, right? So this is actually also the fun part, so we can revisit these things and then go and see if we can really understand it. And I really feel this is the fun part of economic engineering. If we have an economic interpretation of all these things, it makes it so much easier to understand what Newton is really saying. And in fact, Newton used a lot of terms that we would use in economics, like a motive force. He thought of it as a motivation of a particle. Now, nowadays, a philosophical science would call that anthropomorphism, and that's not allowed if you talk about inanimate objects like bodies, and you do scientific work. We are talking about economics, and we're talking about real people, so we are allowed this anthropomorphism. And we will leverage Newton's idea to the fullest. And I think the fit is really well. Now, I think it's fair to say that without Newton's laws of motion, there wouldn't be any mechanical engineering. This is when mechanical engineering was born, is with that publication of his Principia. That's where he wrote down those laws. All right. I also think it's fair to say that without Faraday's law, the maximum interpretation of Faraday's law, the analog to Newton's laws for electrical engineering, there wouldn't be any electrical engineering. Now, without mechanical and electrical engineering, there wouldn't be any engineering whatsoever. All right? So Newton's law is really at the center of this. It's a huge break. That's really what I want to get across with this set of lectures, just how important that is, that perspective. And what Newton did is he defined once and for all what a force is. All right. Now, of course, the word force is an older force. In Dutch, it's kracht. It's also older, but it was used in a more qualitative sense. And people wouldn't know what it really meant. It's like the word impulse. It's impulsion. It's also used in a qualitative sense. In English still, and the technical thing is what we call momentum. And it's a momentous achievement to give a scientific exact definition of what we mean by it, and then it just works. All right? So this is Newton's contribution to mechanics. And Maxwell's contribution is to take that idea of Newton, and Newton called it his motive force, right? And turn that into something equivalent to electrical engineering, which is the electromotive force, or EMF. And with that, he was able to get electrodynamics off and running. They had electricity, but it was not dynamic. You could draw a spark, and that was about it. And they had some magnets, and they could play around with these and get some stuff to move. But they didn't have electrodynamics, and they could change the motion of the flow of electricity. All right? This is the big contribution. So what we want to do here is lay down what we mean by economic motive. This would also be an AMF, so that's will be confusing. Of course, it isn't. And we're going to find out that we have much better names because economics is a very nice discipline. You don't have to grope around for names. They're there. You can say it's a want or a desire or an incentive. We're going to come up with all kinds of different names for different situations. Level of desirability, right? Dutch behoefte. They're all going to be sort of economic forces, and all of these we will be able to place and define exactly what we mean. So that's the real point of this paper. In a sense, when you know what the force is, the rest is details. Okay? As soon as you have a definition of a force in mechanics, you know what a spring does, you know what a damper does, you know what it is. You can define kinetic energy. When you have kinetic energy, you can define potential energy, you can define heat, you can define air. That's the incredible. Right? So as the saying goes, just know what a force is and the rest is details. All right, there's a lot of details. We spent many years studying mechanical engineering to figure out all these details, what momentum is, what all of it. But this is nevertheless true. It all starts with the idea of a force. All right? So that's going to take us, I believe, 2 lectures to get there. Because the first thing we're going to do is put down a whole bunch of definitions, and then we're going to get to the laws. All right? And the next slide, I'll discuss exactly what we do. Okay? So that will be these 2 lectures, and then we will develop these ideas further. So we'll do this on the line what Newton did. So as soon as he's defined his force, he starts figuring out how to do gravitation. That's what he was interested in. We're going to be less interested in gravitation. As mechanical engineers are more interested in elastic forces like spring force, with statics and strength of materials, or friction forces when we do dynamics in real world scenarios and that kind of stuff. Newton, he worried a lot about gravity and circular motion and centrifugal forces. So the development part will deviate a little bit from Newton and just do the regular mechanical engineering undergraduate level springs and elasticity. All right, right? And then I have a bunch of applications still at the back. And we'll take some simple systems like second order systems, figure out how we can look at them economically, like traders, dealers, future traders, etc. Just some technical examples to give you a flavor of how you would simple application of this. Okay? So this is going to be quite a ride, and there's a lot of details. So these are the, this is explaining the introduction to the paper. So here it is. Here's the introduction. So you can read that. So the introduction first lays down what the issue is, what the thing that's lacking in economics. So the first thing you have to see that we're not going to just talk about economics, but we're going to talk about a subpart of economics. It's called the theory of demand, or the theory of demand and supply. It's really what you get at high school or secondary school or grammar school, whatever you want to call it, in whatever country you're from. And the typical lines that are crossing with price and this is demand and supply. There are other economic theories about maximum utility or this or maximum profits. We're not going to touch that. We're just going to look at this theory of demand. Okay? That was laid down by a guy called Alfred Marshall in the 19th century. Here's his book called The Principles of Economics. But the ideas were there before. He kind of put it together. First to draw these demand lines, things like that. But these ideas, they started with Adam Smith, I think. That's which century is that? 1517. Those are the 1700s, right? Somewhere. You can see why we don't use Latin numerals anymore, Roman numerals anymore. This is much older, right? So this, okay, no, this is later. So this is 100 years later. This. And if you look here, this is Newton's book called the Principia. This is where he first published these books. This is what we call like one of the first passages. Stunningly, this was written in 1686. Okay? I think this is not even the first edition. This is the edition by Samuel Pepys. You got a diary that's famous. 1686. That was a long time ago. And it's an incredible book. I mean, very few people read it, but I went ahead and read it myself after having spent a whole life not reading it. And it's amazing. There are very few things the guy didn't understand. And there are many things that have been repeated by people in a wrong way. All right? Like they say, the law is F times F, F is M times A. That's just not true. A lot of stuff that we say is just not true. So it's going to be kind of a journey through. It's a phenomenal book. You can get an English translation online. It's really easy. It's pretty easy reading. Surprisingly so. Anyway, if I compare the Newtonian mechanics versus the theory of demand, there's 2 points I want to make about the comparison. The first point I want to make, and this is important because this is that both theory are what we call causal. A causal theory is that there is a cause and an effect. And many economic theories are not causal. In particular, all econometrics, almost all of it is not causal. It looks at correlations, things that happen together. But you don't necessarily identify one as the cause of the other. All right? So you hypothesize that later. So, as you can say, so if you have a regression line, all you'll know is that you'll have 2 variables and the 2 are correlated. You calculate a correlation variable. But you can hypothesize that one equals the other, but you don't know that. But the theory of demand is causal in the way it was put down, and it still is. So in the theory of demand, what you say is that a price change is the thing that causes the increase or decrease. Okay? So when the price goes up, people ask less, and when the price goes down, people ask more. Cycle. Supply is exactly the other one. All right? So it's not the supply or demand that causes the price change. It's the price change that causes the change in the amount that's demand. That's the way they look at it. But weirdly enough, what they do when they draw these supply and demand graphs, they'll put the price here, and they'll put the quantity demand in there, and then they'll, draw something like this, but they read it like this, all right? It's a little bit of a weird thing. We have to be called them to do. So keep that in mind. This is the cause, and this is the effect. All right? Yeah. So it is a causal theory. Okay? This is not a causation. Now, if you look at it in Newtonian mechanics, it's also causal. The change in the motion is caused by a force. The force is not caused by a change in the motion. This is impossible. You can't take a mass and make it change its velocity. You'll need an infinite force to do that in 0 time. It's impossible. It's not causal. Huh? You need to apply a force in order to change the mass. If your car isn't running and you have to push it, you can't just, change its velocity and then see, what happens to the force. Now, you've got to apply that force and then see. The mass can't just change its velocity at all. Okay? So it's a causal theory. Right? So both theories are causal. So there we're okay. Now, what is this price change in the theory of demand? Nobody, and how does it go? Nobody really specifies that. Right? So if you have these demand and supply lines, you will say, all right, we're reducing the price, so we'll end up over here. But how that process goes in time, Nobody really talks about very much. Okay? So insofar as these causes are concerned, and there's some kind of feedback loop where there's, prices then influenced by something else, nobody can tell you how this process happens over time. In fact, economists will be quite happy to say, well, I mean, this is where equilibrium is, and I just know when it's out of equilibrium, it will get there, but I'm not going to prescribe to you a differential equation as to how it gets there. All right? So systems where the forces and the momenta consequently change over time is what we call dynamic systems. All right? If you just change the velocity, that's not necessarily very dynamic. That's a kinematic solution. It can be just the kinematics of a robot. You say, that's velocity here, velocity there, whatever. But it has to be that the momenta and the forces change over time. Then you have a dynamic theory. So Newtonian mechanics is a dynamic theory, but the theory of demand is not a dynamic theory. All right? So there are no differential equations in time telling you how the price will move and how, as a consequence, the quantity demand. All right? That's exactly what we are going to, the hole we're going to fill with this theory here. We're going to show that Newton's solution to how the force changes and how the momentum changes can be applied to economics. All right, I'm going to fit the economics in the Newtonian theory. You can later on argue that some things don't fit or it doesn't really, but that's not the point I want to make here. I just want to do the same to economics what Maxwell did to electrodynamics. So I'm going to sidestep the question what's really happening, like, I'm just going to assume this is the case. All right? So think about this. Anybody see a current go? Now, you can imagine electrons going, but that's actually wrong. Electrons don't go. The charge that accumulates, and then the other percent on the plate, something else. Nobody really knows if there's anything moving. Nobody's ever seen it, so there's something moving. You just assume that there's something moving, and that thing is regulated by the voltage you put on there. So that's the attitude to take here. Now, I actually believe it fits pretty well, and we'll see this. But there's also a way of thinking. You can't just say, well, it isn't true because I made a measurement or this or that, right? So what we're going to do is take economics, no matter how complicated it is, and try to fit it in the mold, all right? So you've got to go along with that program. You've got to be an engineer about this thing, all right? You're not an economist. You just say, okay, that's my theory. I'm going to see how far I'm going to get, all right? We'll do this. Okay? That's what we're going to try to do, and that's what it's all about. So we are drawing from these publications primarily. So there's no advanced works or anything. With this publication, I really wanted to go back to the sources. The sources in economics are Adam Smith, and then with this guy, Alfred Marshall, and of course for us, it's Newton. All right, that's the exercise. So Newton begins this block, this Principia, two chapters. One called definition. It also has a scholium. I'm not quite sure why that's different. So I'll just call it definitions. And he lays down a whole bunch of definitions. Now you would think that's easy reading, but it isn't. There's a lot of stuff already here. Because a lot of these theories, the laws are not that much. And just often you'll see it's a question of making the definitions in a clever way, and then the laws are really easy. All right? So there's a lot going on here, okay? So we're going to spend the rest of this lecture just on these definitions, okay? And then you will see, actually, his laws, if you look it up, it's just 2 pages or something. He just writes them down, okay? The definitions are pretty long, and then the laws are almost nothing. And then he goes on, and he does gravity, YouTube, all right? Okay? So then next week, we'll do these laws, all right? Okay, and then after we're gonna and then you can have Newton's law, so you know what the force is, but then you still have to develop it. And so you have to get other things with force laws and do that. So springs and masses, you got to figure out what the economic equivalents of those are. And that's what we call price drivers. You can call it many other things. All right. Huh? And then we'll look, the other thing you can do as soon as you have Newton's law, you can start running. So one of the things that you can run is define what energy is. All right. So as soon as you know what force is, you know what momentum is, then you know what how much energy is in there because you know the momentum. So it's a half times 1/m times p², And so you can define what mechanical energy is, and we'll see it corresponds to something called the economic surplus. That's also defined by this guy, Marshall. So when we have energy, when we're really doing well. All right, we also have momentum. So then the other thing that is on that is to figure out an equilibrium. So economists think of equilibrium as a price equilibrium. So prices are equalized. But in mechanics, that's not the case. Equilibrium is when the forces balance and there's no resulting force that causes a change in the motion. That's when you do statics. So it's a different notion of equilibrium. And there is a question of how the concept of equilibrium as phrased in the theory of demand corresponds to the type of equilibrium that really is dynamic equilibrium. So I want to spend some time doing that because there's a lot of confusion about that. So, students may think, okay, this is all very well, and then when they have to do equilibrium, they just pull out the economic definition, and you have to be kind of subtle about how this works. Okay? So we'll spend some time on that. Then we'll do some basic economic engineering, all these simple systems. Okay? So you'll find a more detailed discussion of these points. And actually, it's not more detailed, it's detailed in different things. All right? Okay, so let's get going. So here's a summary of where we're going to get. All right? So here you recognize all the main concept of mechanics. So you have to know what position is. You got to know what velocity is. Then you've got to know what acceleration is. Otherwise, you can't even write. And with this, you can write down things like F is M times A. All right. If you know what a force is, then you got to know what the mass. So that's the Newtonian mechanics in a nutshell. Three things having to do with the kinematics. How the thing moves, where it is, how fast it's going away, and how fast, how rapidly you're changing the velocity. Those are the three ingredients, right? You need position. And then about that, this is what we call the kinematic part, and this is what we call the dynamic part, right? So if you have some robot or something, you can describe it, where it is, how it's going, and how fast it's accelerating, right? But then if you want to bring the dynamics, you bring in the causes of the motion. So you have to say, okay, on the actuators, what forces are acting on it? What's the momentum that each limb has so that it doesn't have overshoot and that kind of stuff. All right? So these are the concepts you need. All right? This is the concepts that we'll be going through in the definition. And Newton does this. Right? He goes through what position is and velocity. I'm not sure how much he deals with acceleration. I threw that in. Huh? He deals with momentum and he deals with force. And he defines a force. It's a little bit weird without defining it. He just says what it is. He goes into the definition, but really the definition is in the laws. So you see he's struggling also a little bit on how to do this. And knowing a mechanic is a bit of a struggle because it all seems circular, huh? And then it isn't. All right, so, all right. Now, put the two, here put the economic equivalents. Now, there happen to be two. This is the ones we'll be dealing with mostly because this one corresponds closely to the mechanical situation. But this one is a different one And it corresponds much better to what you do in electrical engineering, right? So you know, there's a difference. There's these analogs between mechanical engineering and electrical systems, okay, mechanical. However, whatever is parallel in a mechanical system is series in an electrical system, right? So there is one little twist that it works differently, right? So if you have an electrical element, the current goes through it, right? But if you have a mechanical element, the velocity doesn't go through it, okay? The force goes through it, and it transmits the force from one end to another, all right? So you flip it. There's a flip there. That causes all kinds of confusions, you know? So if we see a force as a flow, and all the force flows down, and it's a flow of momentum, they see current as a flow, right? That's what they call it, current. And then they see the flux, the magnetic flux as a sort of a level. We'll discuss this later. And I want to work my way through this part, and then at the end, I'm going to tell you how this works. Okay? So, and in practice, what we'll do is you often do a mix and match. So instead of value, you use the word price. But instead of desirability, we'll say a want or something like that. But nevertheless, it behooves us to be quite specific what the differences are, and then we can be sloppy later. As long as we know, all right, that we're doing it for ease of communication. So I'm just going to go, you don't need to remember this right now. I want to go back to this all the time. I just wanted to pull up it down on the screen. This is what we need to go through. You see, it's going to be a task. All right? So even before doing this, I'm going to define one more first concept that's not even on this thing. And that's the idea of inertia. So Newton's law is also called the law of inertia. And Newton was kind of the first to figure out what inertia was. He coined the terms. All right? And what he noticed, what he noticed was that massive bodies have a tendency to keep moving by themselves. Okay? This was so no force was required to get it moving. So the force was somehow inside of it. Okay? He called that the inherent force. All right? Now, it sounds all weird to us, but now transport yourself back to the day just before Newton published this. And then they had this guy called Kepler. I'm sure you've heard of him. And he had these planets. People were watching these planets forever, you know, in all kinds of cultures. And they saw all kinds of movements, and strange things, and they saw Brion's belt and some kind of frying pan, I don't know what, right? With a Big Dipper. I don't know. Every culture has their own thing. It's been cool. And he was the first one to be able to describe it mathematically using an ellipse. You got the sun here, and then you have this ellipse, right? And you have these Spectre's laws, this thing moving, and then, you know, he figured out they move in an ellipse. And he also figured out what the speed was because it had to, you know, preserve this area. But he didn't know why. He just had a description, right? But it was a momentous achievement to get all these data for thousands of years and then write it down in a simple equation of an ellipse. So in certain cases, when the sun was in the middle, you know, he would have a perfect circle, right? Okay. But he couldn't get to, we all know now that if you're unlucky, the thing might just do a hyperbola, you know, go like this, right? He couldn't do that. Right? Because data is not going to tell you that. You're going to see this thing for once in the millennium, called something called going by. We're going to take historical data to fit this, right? So he can only do the ones that are, you know, bound in a bound trajectory, right? So he did ellipses and these, all right? So he has this like plan of moving along like that. Well, then he had to say why they just kept moving, right? Why Why don't they just stand still and crash against the earth or something? I mean, if I take a ball and I hold it and we go boom, it's going to fall against the earth. So you know what he did? He imagined that there were angels. He was a very Christian man, and they're flapping their wings, and they're the ones who are causing this thing to stay in this trajectory. That was his cause, all right? So notice what happened here with Kepler. He did more of an econometric thing. He just got a huge pile of data of stuff that he could repeat, right? So some stuff he couldn't repeat. Those are the trajectories in hyperbole or parabola. So I think, well, he wasn't able to look at those. And then he fitted that. But then somebody asked him, well, why is it happening? And then he says, all right, that's God doing this. And it's these angels flapping their wings. So this is unsatisfying, right? To say the least. Not really a cause. So then Newton came along and he wrote down his law. If you believe them, and this is why this book was, why I was so busy with the centrifugal force on these gravity, is because he used this law to predict the motion of the planet. So he got Kepler's equations out of this one law. Okay? Get two laws, law of motion and the law of gravity. So this is a stunning development, right? I mean, whoa. And he knows, okay, the cause is this force, all right? And then he dispensed with the idea that you needed these angels flapping. The way he did that was by introducing this idea of inertia, right? The thing will just keep moving by itself. Right? You don't need a force to keep it moving. You need a force to change the movement, okay? And if you do that, if you press on it, the force will kind of go in there. The stuff that goes in, that's what we call momentum now. The accumulated momentum. That's the picture. Okay? That's the picture that Newton creates. All right, that's why he writes down F is P dot, because there's a flux. He calls it the flux. The flux is Latin for flow. So the force is a flow of momentum that goes in there. And once it's in, it's there. That's what he called the inherent force, right? Now, this may all sound like, okay, great. This explains a lot. But now take this stuff and bring it to economics, this way of thinking. Right? So what I'm going to say is, if inertia keeps a massive body moving, what would be the equivalent in economics? Okay, the movement, we'll talk about it in detail later, but the movement, that's the flow of goods, say so many barrels of it. Now, in principle, that won't keep moving. You know how to measure. But if it keeps moving, what is there? What makes these barrels of oil move from some big, random one? The idea is that that's the presence of demand for the oil. So if there is demand for the oil, then you will get this movement of oil going. All right? It's just the presence of that demand. So what demand does, it functions in the same way as inertia does in mechanics. Okay? It maintains this flow, okay? It's just hard to change. So our first analogy is going to be that the concept of inertia is exactly equal or analogous to the concept of demand, all right? So if there is inertia presence, and we will draw it like this here, like mass, that just means at this point, there's inertia present. And you've got to kind of suspend the belief what this is. This is not a regular space. There's going to be a different space, and we're going to have to get there. But first, we want to sink in this concept of inertia. Right? All right, here. Boom. So here there is some demand. I don't really care if there's a person here doing it, or a company, or something else. It's just something. It's going to be ultimately some natural person because they'll do the demand, but something that's causing this that thing to maintain that velocity, right? Now, if there's inertia, you can measure the inertia, right? On what inertia? And inertia is a phenomenon, and the mass is a measure of the amount of inertia. Right? Often we confuse these two terms, okay? But they are different. Mass is a measure, and the inertia is the phenomenon. Okay? Now, in the same way, we're going to have demand, that's the phenomenon, the amount of demand that is there, all right? Now, we will find out that this is the right choice. It's the price inelasticity, okay? The inverse of the mass, that's the price elasticity. So it makes it easier, you know? If there is an inertia, it's harder to do, so it's very inelastic, all right? That's the intuition. This is going to correspond to this. So there is a subtle difference between inertia and mass. Inertia is a phenomenon, and mass is the measure of that phenomenon. All right? Okay? The phenomenon is demand, and the measure is the elasticity. Okay? So price inelasticity is proportional to demand. And the elasticity is just the inverse mass. We don't have a good name for this. Very important. Really, Newton's choice is very unfortunate. To take inertia, he should have taken this because we'll find out why. There's a couple of unfortunate things. This one is the non-causal one. This is the causal one. Because when we draw PV diagrams, we also draw the wrong way because we know that momentum causes the velocity, okay? So we're also drawing it the wrong way. And then if you do it the wrong way, you get the mass, and if you do it the right way, you get the inverse mass. Well, whatever. We'll come to this in more detail. But it's too late now to change, to change something like that's so ingrained, okay? So we'll work with mass price inelasticity, right? Okay. All right. And then you can say, okay, I'm going to locate this amount of demand, or I'm going to locate this inertia at a particular point in space. Now, again, I haven't told you what the space is in economics, but you can imagine doing that. And that is what you would call a point cloud. We do here. So we don't have any extension. All right? Newton didn't look at rotary motion and moments of inertia. Euler did that later based on Newton's laws. All right? He just looked at point particles. Because then you have to look at the Earth, and you have to put all these point particles together, and they haven't developed the theory of integration, so then you have to develop that too in order to integrate this. Crazy what the guy did. But anyway, so we'll think of a point particle. We use that too, right? So when we draw something like this, we don't really mean that it's going to rotate. We just think of it as one mass, it's a segment, right? And in electrical engineering, they do that too when they draw this kind of thing. They just say, okay, this is a location where you have inductance. And they would call this a lumped element. We call this point particle. And we'll just call that the thing itself, the inductor, as the inductance, right? We'll call the thing that has the demand do. It's just some terminology, that makes it easier to do engineering because we think of these components, okay? All right. So this is just some terminology, that. Here's a quote by Marshall. He talks about the elasticity of watts. Nowadays, it's called the price elasticity, but this is, in a sense, nicer, and we'll find out why. Because a force is a watt, not a price. Price is momentum. But that is a nicety. What he's saying, the amount of the commodity demanded may increase much or little according as demand is elastic and inelastic. So you see this idea that elastic and inelastic things are the things that cause, they are similar to mass, because that's the change of the motion. This will be the velocity. This will be the mass. Okay, this will be inverse mass. You see, intuition is exactly that. That's why the
difference between wants and demands.
Yes. The method is inertia. Want is a force.
Yeah.
Big difference. We'll get to, you see, the problem in this kind of exposition is I'm going one by one by one, and they all kind of hang together. So you kind of have to, go like, okay, I'm okay with this, and then, you see? And the reason I'm doing it because that's the way Newton does it. And I really just said, all right, why don't we just follow what he does and we can match it up, all right? Okay. So, if you write F is N times A, what is this A? You also call that B dot. What does it say? Your want, now will change the quantity that you're demanding. And this thing here will be the inertia, as measured by the inelasticity. So you see, this is also why you see this is not quite right, because this is the cause and this is the effect, right? So you would prefer to write the effect on the left side. I prefer to write, that A is F divided by N. Because then I have the change in demand as a function of the wants and desires, okay? And I'll have the acceleration as a function of the force, right? And this is equal to the inverse mass, that is linear, right? So that's what you see. It's a little bit unfortunate. Okay. But what is weird is that we make the same mistake in the sense that economists make. So we plot these PV diagrams also reading it the wrong way. I don't know why this happenstance is. The economists do this and we do the same thing. The mechanics, there's something weird about this business. We call momentum P and economists call price P, right? Okay. Now, then you'll call this queued, all right, and that is confusing because it's really queued up, okay? And I am so sloppy about that, right? Now, I like to put this here a V just to remind us it's a flow, right? When you say I'm demanding oil, I'm not saying so many barrels, and so many barrels per year. But I find some of these things is so weird. Why? As if the devil toys with us, right? Why would we both make this kind of? Because this is will be the more intuitive way to state F is N times A. Yep. You see what I'm saying? But I've been better than to go against tradition. If everybody writes F is N times A, if you try to change that, then you won't get anywhere. It's good to, while you do it, always remember this is like a little variation. You got to know the rules to be okay with the variations on the rules. Otherwise, then it just gets confusing. And also, the word elasticity also terrible because inertia, the elasticity is a spring, right? Okay, they're elastic or stiff, right? So it has to do with how a force relates to a position, right? You want to call this the price inertia or something, huh? But good luck, Economists call everything an elasticity. They don't make a distinction between inertia and elasticity. That we have thanks to Newton, right? Before Newton, they didn't even know either. They just had a relationship, or whatever. Right? Sometimes the force we call a velocity, sometimes the force we call an acceleration, who cares? Right? So, but it's too late to change it, right? And then, so keep your wits about you when you do this stuff. Okay? All right. Cool with this? All right, let's plow on. Yeah, so then another thing you can do, and this is a little bit, I'm just pointing out how important. This is a formatting outline. I'll see everything, but you can read it. So it should be up. Is that you can ask yourself, what is the business of this point particle? Don't exist. Well, just to say, and later on we'll use it when we'll do some applications. So I just want to make the aside. You can show that if you have a whole pile of these things, and they're rigid, they're only got to be rigid. Maybe have all the masses here in the center of mass, right? So this will be the center of the mass. And then you can treat it as if it were a point particle. That's what Newton did. I mean, he looks at the moon, the planet. Now, of course, this is not a point particle. The planet's huge, right? But from a far enough distance, and it's symmetrical. So if you don't look at the rotation that the thing does, and it's not too floppy, so you don't lose the thing everywhere. It doesn't matter even if you lose it. You can always look at the center of mass, right? And well, you guys know how to do that. You do all those things a bit. You get the center of mass, and that behaves Newtonian as if it has the total mass. And this is something we could call the center of demand. All right, so this is a saying that if you have many agents, many demanders, you could aggregate them. Aggregate over agents and treat them as if they're one, right? Just like Newton did with a planet or something, or what we do when we have a global mass like this floating around. Right? This is my wallet, so it doesn't have much mass. But so that's what they call aggregation. And I'm not going to do too much with this. You can also look at the sum of this inverse mass, and that becomes what's called the reduced mass, and we'll see how that relates to interactions between the agents, right? That's what you use the reduced mass for. Also, if you have two masses together, they may interact by doing this. For that motion, you use the reduced mass, and for the joint motion, you will use the center of mass, total mass. All right? Okay? So this will be the mutual elasticity, okay? And so this is just a bit of an aside. So just to get yourself out of thinking that we're really only looking at point particles, you're looking at anything that you can do. All right? Good. So now we know what inertia is, and it's demand, and we know what mass is, and the price of inelasticity is related to price elasticity. Now I want to tell you what these what's up. So we think of a mass as space, right? Suspended in space. And the space we have is free space, and it has a different position. Now, what will be your position in it? Right? Suppose you're buying apples and pears, right? You bought 20 apples, 30 pears, and then you're still buying or selling. At a particular point in time, what will be your position? What way you will happen to be standing, right? I think your position, if you were a trader, say, on the stock exchange, would be, how many shares of this do I have? How many shares of that do I have? Right? I think your position, it will be, now if you have apples and pears, you just count how many apples you bought, right? And how many pears you bought and sold, the net amount, and that's where she goes. All right? So you start with an arbitrary 0 point. That doesn't have to be some absolute zero like your cupboard where you have these things lying. Just some point of zero, and you start adding up how much apples you buy, and then sell, buy, or till you end up here, right? And where is the so take bananas, right? That's the position. Right? So position space, you shouldn't think of it as the space around you. Think of it as a space where every dimension is some good, particular type of goods, whether it's apples, banana, or money. Money is just a good, right? You can count it, right? You can see it, as long as you can see it, or see it, all right? Or shares, or whatever it is you're looking at, as long as it's observable, all right? So how many of these dimensions are there? 2, 3, 4, are there 4? I'd say so. Right? There are more than 4 goods in this world, right? So this is one thing that's quite different with Newtonian mechanics, right? So Newtonian mechanics only deals with 3 dimensions. Notice, we will have any number. Okay, that's not a problem because technology mechanics also have any number allowed. But you got to see that, all right? Okay. But the other thing you got to see that the Newtonian setup is such that if there's a mass here, it's the same for all directions. That's not necessarily the case with us either, right? So your price elasticity for bananas can be different than for others. This is also not a problem. This is just because if you have like a moment of inertia, it's not necessary that around all axes it's the same, okay? Right? And you can see Euclidean space as just a way to calibrate the dimensions so that the mass ends up. Right? These are things that were built in the beginning in the Newtonian theory. Later on, they were dropped in more general Lagrangian Hamiltonian approaches. But I want you to free yourself a little bit of some of these assumptions. Okay? So it's unclear whether you have only 3 dimensions, and it's also not a priori obvious that all the price elasticities are the same in every direction. You can calibrate them so that they become the same, but that's not necessary. Okay? All right. So this space, I usually refer to as commodity space. Okay? Now, why do I call it a commodity? Suppose that you just keep track of these apples this way, right? So you add some apples, and you subtract some, and then you end up a total amount. Now, when can you do that? Suppose I have here some fine art, one drawing and the other painting, or this Rembrandt and this Giotto painting, right? Can I just add them like that? Of course not. Right? You can't interchange these things. So when you start adding stuff, you know that you don't distinguish between the individual elements anymore. Because addition is a commutative operator. A plus B is equal to B plus A. So, okay. So these goods that you look at, you have to consider them to be what is called fungible. Okay. So they are, you can exchange one for the other, and it will be the same. So oil is fungible. You get so many barrels of North Sea crude, but if you get another quality, it's not fungible. It will be so many barrels of other type of food, right? Silver is fungible also to a degree of sterling silver and Guinea silver. You have to give the quality. But if you give the quality and the type, then you have something that's fungible. Although this is what the economists will call a commodity. A commodity is something like pork belly. They're all the same. When we consider them the same, and you go to Chicago And the CBOE, you buy somebody pork bellies, right? You don't start looking like I want this one or that one. You don't start cherry picking. All right? Huh? Okay. Huh? This is important because otherwise this doesn't work. Huh? Huh? Yes.
Would this then be like a condition for all of the theory that which you're analyzing fungible?
It will be a condition when you set up the dimensions. You can only put goods that are fungible on each dimension. If they're not fungible, you have to get another dimension. You see? Yeah? Okay. So it's like saying you have a motion in the x direction that's fungible with any other motion in the x direction, and now you get one in the y direction. Even if you consider the y and x the same, I don't know why you would, but and then they're fungible, but when you don't, then don't. You see? You see what I'm saying? So it's not so much of a hypothesis, it's more of a constraint on the model for the model to work, you see? So when we Newtonian mechanics models, you can't mix up x and y directions. You can't. You get them mixed up, you know? Because then when you square x and square y and look at the square root, it's all messed up, you know? Because they're not fungible, it's only the squares that connect, right? Yeah? You see? So that's it. It's more of a modeling decision. So be careful when you draw these up. Right? Okay. Now, what you would do is all these dimensions, they also have a name. You can call them dimensions, but in practice, that is what you would call an account. So a business or even an individual, they may have an account at which they keep track how many bananas they bought, inventory accounts, right? So these dimensions we call an account. So this is the apple account, and this is the banana account. And then if you have a whole bunch of accounts and you chart them out like that, you call it a chart of accounts. All right? So the coordinates, what we call coordinates in mechanics will be an account. All right? And a coordinate chart or coordinate frame would be an account frame or a chart of accounts. This is actually a name they use, a chart of accounts, right? Then you chart it out how your accounts are. Okay? Clear? So it's good to use that terminology because pretty quick, if you do economic engineering and you start, you have to be careful you don't talk mechanics, and all your, you want to use the right terminology. And then take mechanics, but talk economics, all right? So a lot of students, they start pulling back into saying force and dimension, and then everybody has to think, oh yeah, we mean, so don't try to avoid that. So that's why I spend a lot of time coming up with good names, right? So here is just a table of some, so you can see motion, you can see it either as exchange. I use the word trade, so move the goods are just moving from one person to another, right? Okay. These words are also quite general for economics. Like sometimes in certain application, they will call this the flow of goods, the motion, right? Or the flow of commodities, and sometimes they would call it the exchange, or so don't be too rigid either. I mean, we are not rigid either. You can say force, but you can also say push or pull, right? And sometimes you just have to, not get too academic about it, and not too stiff, to make the thing come alive. So just take this as a way of, try to avoid too much of this stuff when you do your thinking. But also don't be too rigid. I mean, economics is just a very practical discipline, and in terms for different situations are a little bit different. Okay? But if you look at electrical engineering, there's at least 3 or 4 words for EMF. You could call it EMF, you could call it voltage, you could call it what else is there? I think there's a potential drop. So there are already three for the same thing, but we use them in different things. And EMF will be if you have a battery, potential drop is if you have a voltage, if you sit there with your voltage meter. So it's the same in economics. So keep that. Don't become a mathematician or a physicist. Become an engineer. Right? Just use the word that really. A lot of I've seen that a good choice of words really helps when the research gets understood and accepted. Okay, it's really more important than you think. In fact, a lot of physics and mechanics is difficult because the words, like energy. I mean, the words for is entropy. So you call it entropy, then you really know it's going to be a difficult concept because the word doesn't suggest anything reasonable. And then you lose it again, right? Now they've just chosen a better word. I have a few ideas. Then this will never be fixed. But the word would be such as Sometimes, of course, a picture's worth 1,000 words, but sometimes a word is worth 1,000 pictures. Almost the right word, you immediately you anchor that intuition that you need in order to guide you in the thinking. All right? Okay? Right? So you can see there's a lot of time here spent just getting this right, and also for me, explaining it so it comes across and you make it part of your thinking. This is really important. Okay, because then it becomes intuitive. Then you can grasp it all. Otherwise, you're just working through these equations, and you're what we call a tool with engineering. The guy who can crack equations has no idea what he's doing. So there's a couple of other things. So physical space, just the ambient space we have, that's going to be commodity space. Now, physical space, we think of it as Euclidean space, so you can measure distance. Don't do that here either. We don't even know what it means to be orthogonal, right? Because you need an inner product. We don't yet really have it. We can get it there, but it's extra structure we'll have to introduce. So we'll do it later, But for the moment, you just got to be a little bit more relaxed about what this is. Newtonian Mechanics was built, and you pull down in one big swoop like that, And then later on, people started pulling off all the inherent assumptions, and they made these Lagrangian things, and where things would move and no necessarily look flat, and So it's a bit of a problem that you're so trained to think that way that you've got to kind of relax a little bit. All right, so physical space is a commodity space, but with less structure. Think of motion in the general sense, like the equations of motion or the motion of this thing as trade, right? So without trade and interactions, there's no motion, right? That's the motion. Now, economists never. That's not true, but for economists, the velocity, the quantity is what they call the quantity demand, right? Which often is in the theory of demand is called the quantity demand. In the theory of demand, it comes out of nowhere. You just know it. Okay, so they'll draw price here, quantity demand there, and this is what Marshall here, he draws this. So as soon as you know what price is, as soon as you know what this is, and then you are made to understand what this graph is. This is not the way Newton did it. Okay? And I think he was building on an idea of I'm not quite sure because he doesn't attribute it to anything, is that you can define velocity by looking at the position. Okay? Now, we do this as engineers totally automatically, all right? But it's good to go through how we do it and then realize that in economics is not done this way, and we'll be doing it this way because it's going to give a lot of consequences that are going to come out of this particular definition. So how would we define velocity? Now, formally this works, normally you would say, well, what's the problem? V is just the change in position with respect to time. Now that's great, except that we work in one dimension, right? Because in two dimension, and then we will get a whole bunch of points in, what's happening, right? So then you can get away with it too. But what do you mean by then? Suppose you have a bunch of points, then what would you really mean by it, right? So the best way to look at it is geometrically. Right? So before you know it, you start making all these vectors. You first want to have the picture. Picture is given here. So what you see here is just a demander. Here he is with his central mass, central demand. And he's blind. Apparently he doesn't sell. Okay? I like to say he's acquiring rather than buying, because buying already means well, money going the other way, all right? But I don't want to get too particular on it. So, at this point in time, he has this talk about, he is short, then here, he's over there, and he's over there. Now, what would be, at any moment in time, the quantity he is demanding now, per unit? Well, I maintain it will just be the tangent vectors for this time. Okay? All right? And I will, so that, I would say that tangent vector, right? So that's a directional derivative. So usually we don't write that as dq dt, we write something, I don't know, directional derivative along this path or something, right? It's been something like that, something like that, right? So we don't even use this notation. We try to do that, something weird, so like a directional derivative along this path. So you have to say what path you're going along. So this will be the path gamma, and then you give this so you see already this notation is kind of ambiguous, right? You need to know what a directional derivative is, and then you know that this is this vector, okay? And this will be this velocity vector as a vector, right? But again, graphically, it's totally clear. Okay? So this is what we're going to do. Use as definition of the quantity demand or the flow, right? This is different. Because this is truly a vector. Because it has a 0 point, it can be negative, it can go the other way. And if you have two, you can just add them, right? Boom is, okay? Notice that space, sometimes people say that that's a vector, but it really isn't because it doesn't have a point of 0 to begin with, right? There's a couple of other problems, correct? That's not so important here. So this is a vector, whereas the point is just, the position is just a point. That's a true vector. So we can think of this V as really a vector like that. I didn't do it in the paper because it gets out. All right, so sometimes we make it bold. Okay. So that's different from what economists do, right? Well, it's a number, it's not a vector. They don't use vector calculus or any of that, right? So for us to make that distinction, all of a sudden, the quantity demanded on the flow has got to be a vector. So it's got a magnitude, that's the size of the demand, and it's got a direction that tells you what mix of commodities he or she is buying. All right? So now you can see, you can make a distinction between buying or acquiring and disposing. One you can call positive and the other you can call negative. Right? That's something economists also don't do. That's why they have separate demand and supply graphs. Because here it's just in one or the other, right? Okay. So we'll see we can get rid of these two graphs. That's a little bit later, right? Okay. So at this point, we're introducing vector calculus into economics. Okay, that's the only way we can get this thing to fit. the fit is very good, and it makes everything easier. You get rid of half of the theory of demand because it's just the same thing for negative vectors. You can get negative prices. Yep, it makes sense. Like you said. All right. Huh? So this is the definition. There's another thing that economists would have, and they'll first define the quantity demand. That's the early guys, and then later on, people started talking about stocks. Okay, so here they would have a flow, and then later on they would also have some stocks of stuff. And then somebody says, well, okay, we have defined these two things separately. Oh my God. But this is going wrong. If we don't build that into our models, then we'll have stuff coming out of nowhere. And then they came up that's recently with something they call stock flow consistency. You can look it up, and there'll be big Wikipedia articles on the condition of stock flow consistency, and that these things have to be consistent with one another. What I'm going to try to make here is this problem only occurs if you don't define the flow in terms of these stocks, that are in this physical space, okay? This commodity space. Without a definition, you already have with definition, this is taken care of, okay, from the get-go. Okay. So Newton's definition of velocity we adopt as the definition of either the flow or the quantity demanded. All right. Quantity demanded is just the mobility analog, and the flow is the current analog. I use them. I use them to change it. Right? Then you go to say I use them to check. All of us almost talk about quality demanded in the theory of demand, and otherwise they will talk about stuff. So this is the point you got to see. So our definition, Newton's definition, takes care of this. Okay? It's kind of a cuteness is that all of Newtonian mechanics can be summarized by two definitions: that the velocity is the change in position, and the force is the change in momentum. Feel that? This is by definition. So this is our definition. Feel that? This is Newton's law. This is the definition of velocity. Anyway, the way we set up is this one is a real definition, and the other one is a law. All right, so you see it a little bit, almost a little bit circular. It's a little bit subtle, how it's okay, good. Good. You can imagine that this thing changes too. So a little bit later, the quantity demanded will be different. Okay. Then what we do is a little bit of cheating. We want to calculate that. So this is the slide and this is we just transport this back and subtract them, and then we'll get this vector. It's the difference, right? The rate of change in which they do, and that's what we call the acceleration. And we will refer to this as the needs or the demand extension. This is, we'll see why this makes sense. Needs, okay? So the thing, okay, here's the intuition. If you're just going at a constant velocity, you don't need it. So if you're out, demand, the quantity demand is a constant, you don't feel any desires or wants, you're relaxed. You're just eating so many apples a day, you're breathing so much air a day, you're consuming so much oil, you cry, it's cool. That's good. Now, when you need something, right, then you're in trouble, right? When you want something, you're going to need something, right? So you need to increase that amount, right, that you're asking. So the acceleration kind of measures your needs, all right? And then you'll see that F is A, all it's saying is how your wants, relate to your needs and that they're really disproportionate. Right? So this is just how you, a way of looking at it, okay? You'll see lots of articles by philosophers what's the difference on wants and needs and this. And some of it is quite interesting. But in the end, I've decided just to look at it simple way like this because it's just good terminology. Okay, good. So it just allows us to make a distinction. And this is the needs are set totally in terms of the good. So this is some change in what you're demanding. So it's either in terms of apples or pears. This one has value built in, right? So I don't think needs are value built in. Your desires do, but not your needs. All right. So that's why I chose it like this. It's just a handy way of feeling it, Okay. You got to appreciate a little bit the beauty that FSA is only saying that your wants are proportional to your needs, and then you can stop the whole philosophical discussion like an engineers I want to do, right? Just get on with it, okay? So a lot of these definitions I made, they're really designed to take this Newtonian framework and make it natural, And we don't just talk about economic force and an economic acceleration, that really sucks. It's just not good. All right. So, all right. Yes.
Say you're doing a thesis in like a specific domain.
Yes.
Are you then free to choose?
Yes.
Some things?
Yes. Yes.
Okay. And then for the other question, you have this money space.
Yeah.
Would money also be
Yes.
space?
Exactly.
And like, how would you constrain this? Because you feel like the amount of apples you can buy is constrained.
Yeah. So in real life, space is also constrained, right? And then your wall here. Or maybe a spring attached to this that makes it hard for it to go further. Or gravity, or iron or left, right? So that's the discussion we'll do later. You see, here we just set up the theory, the place where the play, the theory itself, where the play is going to happen. Okay. We're going to say, here, this is the podium, and you can move this way, and you can move that way, And we haven't decided yet where we're going to put the barriers, okay? But this is what we'll call your movement, and this is what we'll call this, okay? You see? And here are some general names. But if you look at money or securities, then usually we call the force a little bit different. We call it a cash flow instead of a commodity flow, or we may call it a flow of credit, There's all kinds of names. Bill will give a presentation where, he has a nice application where you look at various flows of money, all right? And you also have a lot more securities, but Bill has a very nice one, and then you'll see all the different choices that you make. That's exactly right, okay? So all the constraints are postponed, okay? So in Newtonian mechanics, you don't say, okay, I got some walls here. Now let's talk about spaces. No, first tell me about spaces, and then later I'll put a wall there, or remove the wall, put it a little further. Okay? So you got to go with me just for the general, you see? Okay? These are just the general tools you need, definitions you'll need to even make sense of the laws. And then when we have that, then we started looking at specific application and put a wall. Okay, look here, I already told you, well, I have a wall here already, right? But we don't know yet what it is, right? Well, you can kind of infer it's something with an infinite pricing inelasticity. So it's going to be able to absorb a lot of wants and desires and not change its quantity demand, right? That's the idea. So we can think through what that is, right? And in fact, we'll come to something that's called the Edgewood box where they have walls. Okay, good. And the other thing is you're interested in money flows, but now you have to see that it's set up to be very general, right? And you can fill this in. Securities and this, I just call it commodities. And money is a commodity, it's called commodity money, right? And credit is also a commodity because this credit is the same, a little bit more credit, right? Okay. So here we have this velocity and all this, and then we can do the same with our, so I did this for a center of mass. Of course, there's a point particle. You can do this for something that you could call a central demand, and you can look at the aggregate demand of a whole bunch of people in the economy. As long as that works, you're fine to look at the aggregate needs of a group of people, okay? Don't waste too much time. Just to tell you, it's not too narrow, okay? Huh? So don't panic at this point. Let's keep going. So that was the kinematic part. So we know what position is now. That's just how much we've bought and sold, how much is on our accounts, which will keep track of things, okay? That could be a bank account where you keep track of your money. It's going down. That's the account. That's the dimension, right? Then I can see how much is going in, right, and out. Those are the transactions you're doing, right? That's my velocity. And then I can see also how I'm changing this by the accelerations, right? So it's an expression of my needs, right? How I'm changing my transactions. I'm going faster. I'm buying more and more and more and more apples per day, right? Well, that's changing my demand, right? Okay? That's all kinematics, okay? Now, most of economics, I'd say, is purely concerned with kinematics, so the flow of money. Nobody talks about the price of money. They do a little bit, they call it the interest rate, but really nobody talks about the force of money. It's getting much harder. They have something called the force of interest. This is the dynamics part, and this is where it really gets interesting, because this is what you need to do dynamics, motion. You just need this causal motion. So what we're going to do is we're going to set that up the same way Newton does, and we're going to find the definitions for the analogical momentum, okay, and for the force. And we're going to just do that with definitions, and then later with the laws, and next week, this will be clear why this are the right definition. Okay? Now, the first definition is that of price. Now, you can kind of intuit what that is, because if you look at the velocity, and you have a mass, and this is the moment, right? Yeah? This was a law, not of Newton. This was a guy called Descartes who showed up with it. Newton just took it from Descartes. In fact, what Descartes said was this. You have a problem. So he was looking at a way to measure something that we call the quantitatis motus, the quality of motion. Now, they knew it was moving, the velocity, but they wanted to quantify the amount of that motion. They would measure the amount of motion. You know, it's like they knew it in inertia, but they used the mass to measure the amount of inertia. And now you want to measure something, a real number or some number that gives you the amount, okay? Now, Descartes, he got a long way, so he wrote this down. Some people wrote this down. That's, I think, Leibniz wrote this down. Okay? This looks more like energy, right? This is not looking like momentum. The problem with this is there's a half this, and we'll get to that, right? That was Leibniz. All right. And the problem with this is this absolute value stuff, you see? Because it kind of measures the amount of motion, except motion to the right and motion to the left is the same. So if you would have an explosion, so the thing is standing still, and you explode and it goes in two pieces, then you would have created motion out of nowhere. Because you will have some positive stuff going to the right and some positive stuff going to the left, and you allow and the point you have nothing because the velocity was zero. Right? This didn't work because you want a conserved quantity. If the quantity is not conserved, how are you going to track it? You know, you got to track what's going in and what's going out. Okay, so this wasn't working. And then his friend, I don't know his friend, but they were both living together. So his name is Alphonse, and only we know how to pronounce it, right? He fixed it. So he says, look, this cannot be just a positive number. Yeah? So you got to take away these absolute values. Right? So this thing can be, if this is negative, this is also negative. And then later, people fixed it because then vector calculus was developed. And they said, well, this is a vector, this is a number, really this number, it's a tens of it, but we can assume it's a number, okay? Then this must also be, and it must point in the same direction as, the velocity. So that was the choice he made. It's a little bit unfortunate that it would have been better than the minus sign here. But this is just what our Arabs did. All right? Okay? Now, if you do that, all this will be the law you get. Okay? So all you need to do is decide what the positive direction for the velocity. You multiply, you assume the mass is always positive. You could have assumed the mass is always negative. It wasn't done, but you get a perfectly valid Newtonian mechanics. Okay? And then you will know what the momentum is. Okay, and if you do that in multiple directions, this is just a relation between vectors. Okay, right. Now, this you know. You didn't know the history, but this is you know, right? Yeah. And you know this is a vector, and this is a positive scalar. Now, let's compare that to the, and this momentum is what we now use as the measurement of the amount of motion, okay? The momentum in the vector. Now, what was motion? That was the train here now. Okay? And what would be the amount of motion? How can we measure why stuff is in demand and not in demand? I maintain the price stuff. Right? So the higher the price, the more you know things are in demand. Okay, that's just okay. So we can think of price as something that measures how much. Okay, so we had this interesting discussion before this was full. How the concept of momentum was developed is something that first was an attempt to measure how much motion there was. And first they had just a real positive number, and then they fixed that, and it became positive or negative, and then they fixed that, and it became a vector equation, right? So you get this equation. Okay? Now look at economics. So here is this is what Marshall did. This is out of his original work. This is the supply and demand graph. All right. Now if you go to a secondary school, they'll pull out here the quantity demanded. They'll put here the price, and they'll draw a line like this, and they'll draw a line like that, right? Cool. Huh? All right. So you see, if you draw this equation in one dimension, you're going to get this, right? Here's P, here's V, so this is a negative V. Huh? This is a vector in one dimension is either a positive or a negative number, right? Or zero. Okay. So you see, you're pretty close. So the intuition of price as being this quality of motion, but then the motion of goods is what? The intuition behind it, there's a couple of little problems, right? The first problem is this thing slows down. This would look like a negative mass, right? The other problem is they don't go through zero. Now, we're going to fix those problems to move on, okay? Now, the first problem is fixed the same way Huygens fixed Descartes' problem. As soon as we see that this is a vector, we solve the problem of this going down. Because we'll call supply positive, we'll have to call demand negative. Okay, if you turn it around, that's also okay. So then you will see this thing has to flip down, right? And you can just turn around. Okay? All right? Okay? So then you go flip this around, and then you'll find that it's going like this. And you see this whole crossing line stuff is already not so cool. Now you still have one more issue, namely that there's going to be, it won't go through the origin line, you know? So what do you do? How do we deal with that? I'll tell you how we're going to deal with that. Suppose you have some mass that's moving, right? So a certain amount of momentum. With respect to move, do we all agree on that? Suppose I'm moving along. It has momentum for you, not for me. No, measure the velocities in one. We're sitting on this earth here. We almost have momentum is zero. But somebody standing on the moon looking at it sees it spinning around like a maniac, you know, with a huge amount of momentum. Right? Okay? If you're in a train and you take your wallet out, you will say it has no momentum. You drop it, you'll see it drops right out. But something else, you see the wallet move with an amazing velocity, you know, not amazing, maybe if you have to stop time, you know, it's not going that fast. So if you do the events in general, it may not go that fast, you know. So the point I'm trying to make is momentum depends on the observer. Okay? You can take any value and just reduce it to zero. If you So what is not done in economics, and what we will do, is to take one location and call that the location of zero demand, right? Zero quantity. We also call this an inertial reference. All right? We'll come to that when we do Newton's first law, but that's going to be the solution. Once you do that, then you'll see that with respect to that frame, the thing, it will always have to go to zero, the demand line. It will only differ in the price elasticity. Okay? To be very disciplined in doing this kind of stuff. This is what the laws that we'll do next time will take care of. Now we just assume we can do that. Okay? Now, if we, for the moment, assume we can do this, and it will all be justified, we can take these economist demand lines and then turn them into what I would call as a unified demand schedule. So the line is here, you know, the demands are here, suppliers are here, there was on the negative. I could have changed it around, right? You can call right positive or left positive, doesn't matter. And if they have the same price inelasticity, you always get the same brand. Okay. You can think of price also as a vector. So we'll say the bid zero positive and the asking price is a negative. That's all we're doing. Okay. Okay. Now, this is something to let sink in. So sometimes, most of the time, you think of a price going negative is ridiculous. It cannot happen. If you think of a zero price, it's just when somebody happens to go zero and you happen to go zero. That's not the point here, right? It's a zero, that is, that price is precisely zero because you're going along with it has the same quantity demanded as that reference. Therefore, there is no trade, so the relative price is going to be zero. You don't feel any trade, need to trade. You both want the same amount of apples, and it's not like somebody is demanding more than the other. Okay? This will all be made clear in the next section, okay? But you've got to kind of let that sink in, that our notion of price is a vector that is defined in this, okay? All right. Is that clear? So we get rid of this thing, and we put it into one of these. And if these are two different persons, there's no reason that this should be the same slope, of course. It could be this guy. We won't divide like economists do the world in demanders and suppliers. We'll assume that anybody can either demand or supply, right? Right? They don't do that. They assume some are only buying and some are only selling. No. We could buy or sell. And then the buying or selling is with respect to some other reference. So if you're buying, but you're buying less than the reference, then you're really selling. Okay? This is going to be something you've got to let sink in. Okay? But if we don't do this, there's no way to get it into the Newtonian framework, and we'll always be still Mickey Mouse here. Okay? And I'm not. Okay? So we'll develop this idea a lot further. So this is what I call the unified demand schedule. This is these things now. You can see how this all corresponds to how we would look at it, and how this will be a demander, this will be our reference, some huge markers, that this market demand is this, and then we'll measure if we're from demanders, if we're in excess of the market, and we're suppliers, if it's in deficit and below the market, right? That we're supplying. This is just a choice, okay? Now, the last thing you may notice is that these lines are curvy and our lines are straight here, right? Now, that's really not a problem. That's part of the law. I mean, this isn't just Descartes who came up with it. There are many other definitions of momentum. So you have photons, they don't even have a mass, but they still have momentum. So you can't even write this down. Then you have a lot of relativistic effects. So, this equation doesn't work either because it works only with rest mass, so with very low velocity. So I don't want to have you guys worry a pretty head about that right now. So the fact that this curves, we'll deal with this later. Okay? It could also be that things are changing, and then the mass is changing, and then therefore they measure a curve. There are many, many reasons why they may have it. So one thing you have to understand of Newtonian mechanics, you just kind of make this assumption, okay? And you go with it, and everything that then you see is different must be due to some other effect, okay? It's only when that really doesn't work that you have to ditch this, like when you're in quantum mechanics or relativistic theories. But we'll do some of that, okay? But for now, this is what these things are going at. All right? Okay? Okay. I think we're going to make it. Oh, I made a mess of this. I was going to fix it, but I didn't. So maybe because I made a mess of this and I want to fix it, I think this is a good moment to stop. Okay? Because it's quite a bit of material, and then we can finish this this section next time, and then move on. All right. So, any further questions on this issue here? Actually, a lot happened here on this one slide. But because this usually depends most of the utility, the kind of the reinterpretation of what price is. Okay, really being defined. This is a definition defined in this way. So you know what this is, right? We define this. We already define this, and we just say this is nice. Okay. Huh? Okay, so I'm saying, well, this is zero. It's also the price must be zero. Huh? Well, this is negative. This must be negative. Huh? That's just what we say. And then we roll with this. Okay. Huh? Okay. So this is a lot of times counterintuitive, but maybe I'm repeating myself. But it's important to see that this is the only way this whole business is going to work out. And in a sense, you can see how it should be the only thing, because these other guys already tried it. They tried it. You know what? And it didn't work. They weren't getting it. And Newton saw that. He didn't use this definition. He used the other one. Right? They also tried this. Just to get a positive. It didn't work either. It turned out later that this was the energy, the economic surplus. Okay? All right? So they tried all that stuff and it didn't work. So you got to have kind of peace with that idea that if they have tried it and it doesn't work, it's not going to work here either. Okay? Huh? And you can try this in electrodynamics, it also won't work because the flux linkage is just the inductance times the current, not the absolute value. Right? If you do that, it's not going to work. Now, no electrical system will work. All right? And it's the flux linkage, the magnetic flux, you can't get it by doing this either. All right? Okay? Huh? So that's the trick we always play here, right? So we try to track the development of mechanics. That's why I go back to Newton and the history of it. And then see if we do that, where economic stops and which idea of little brilliance we can use and then move on. You know? Because at the time, to think of momentum as a vector and a quantity that's not positive wasn't big leaps, you know, you can think of it, you know, but it was a big insight, you know, you have to get used to that the quantity could be a negative thing, you know. It's just, so this is the same that's going to happen here. The price can be a negative thing. That doesn't mean that it's a bad, it just means you're on the other side of the bid, you know, your ants came off. That's all it means, okay? So, we'll stop here.